Okay, so there's a few more loose ends, and I want to go back to and remind you what an exponential is in the context of orders. And there was something that nobody solved in the exam. I mean, I think I know at least one of you tried it, and they asked for a hint. So let's solve this thing. Exponentials. So what does it mean to have an exponential in the context of an order? And the idea was that it's something. What it does, what does it do? First of all, I will denote it either like that. Okay, let's use lowercase letters, or like that. But I mean, don't think this is some kind of proposition that A implies B. It's a binary operation, just like A plus B. It's written like that. But the idea is that it will encode the information that A implies B. If I think of this interpretation of order, where we saw that when I write something like that, we can see it, we can interpret it like this. And in this case, the exponentials will end up saying that there is something that internalizes this external notion of probability. It captures this idea, and it's the same thing that happens in like when you're doing sets. You have functions from A to B, but you also have a set that captures this idea of functions from A to B, and you usually denote it like that, or like that, the function space from A to B. So you have sets, but you also have the idea of an object, a set, that encodes the whole collection of functions from A to B. So it's kind of similar here. You have this idea, this external notion of probability, and in a sense, this thing will be something that encodes the idea that A from A can prove B. Okay, so enough talking. Let's do some writing. What does it do? The main property it has is that if you take it together with A, it proves B. You notice I say proves. I'm writing less than or equal to because I'm in an order theoretic setting, so I write things properly. So this is what it does. What it does. I don't know how I should write it. I'm starting to like this thing because I had a name for the other property always, which is when you define something with a universal property, you say it's the best among those things that do what they have to do. So, okay, I will call this thing this is what it does. And it has to be the best among all those things. And what does that mean? Someone help me? Nobody wants to help me, apparently. So always I get a candidate, I put it in place of this weird object that I'm trying to define, this B to the A. And I say, okay, if something else does the same thing, this is pretty much welcome, pretty much standard, then I want to say here that my guy is better than the other guy, and so in this case, I need to think, what does better mean here? Does it mean that it's less than C, or does it mean that it's greater than C? And as I said, usually one of the two alternatives is completely useless. And now, if I take this to mean you are better, for any A and any B you give me, it will be the bottom element that has this. It will be completely useless to say I will have a binary operation that given any A and any B, it returns the bottom. Just take the bottom, right? So this will not. I just realized that the recording of my screen stopped for some reason. I'll try to save it. It's good that I noticed it now, but I don't know why it stopped. Okay. Okay, so again, this is what the exponential does. Taken together with... okay, I'm getting some errors here. I'll try it again. Okay. Sorry, παιδιά, θα start recording. For some reason, it was trying to record on Discord, and I haven't even used Discord on this tablet. Okay, I think I fixed it, but I'm not sure. Okay, so again, what does the exponential do? Sorry for the delay. Taken together with A, it can give you B. So this is what it does, and it's the best among all those things, which means that if you have any other candidate that does the same thing, my candidate is better. So this would be like the exp best. Okay, so and we have seen that if you have a lattice where it guarantees exponentials, it's necessarily distributive, and we call those things Hating algebras. And the exercise that I wanted to solve let's solve it actually, was to prove that as soon as you have exponentials, whether you want it or not, you have distributivity. And let's remember that we have proven one side of distributivity for any lattice. We have seen that if you take this, D joined with A and B, this is always smaller than D join A, meet D join B. So this part of the inequality is already proven for any lattice. Now I have extra things. I will not lose this, but now I need to prove the other way around. Okay, obviously I need to use exponentials at some point, because I know that there are non-distributive lattices, and the only extra thing I have here is that in my lattice exponentials are guaranteed. So let's see what I can use. Essentially, one way to read this is like, I think some of you have seen this idea of I have like C and B proves something, proves, what do I have here? No, sorry, C and A proves B. This is kind of purification, disqualification. Then C should prove that if A, then B. If you look, this is like passing the conjunct on the other side of the tensile, and vice versa. If on the other side of the tensile you have an implication, you can pass the premise on this side and become a hypothesis conjuncted with the rest of the hypothesis. But still there is something you need to do here. So essentially what I would like to do here is something like, do I have these things right? Yeah, I think I have them right. Pick one of these two. I think I'm missing something, and I have some notes. And if I do, okay, I want to stay like, so let's do the following thing. It would be the same thing. I hope I can convince you about this. I will prove the dual of this thing, and I would not be done. There's another theorem that you need to prove to get the other side, but since I picked one side to do here, and on my notes I have this one, let's do the dual. Okay, let's go back to the dual. This is what happens when I'm not looking at my notes and I decide arbitrarily to pick one side. It's definitely the other side that I have on my notes. So what I have here is, I want to show that the meat of those things is less than this. And I'm not cheating in the sense that since it's the dual, but I didn't flip this, it's pretty much the equivalent that I was trying to prove, because this now holds for any lattice. So now I want to prove the other side, which is this, that is not guaranteed in any lattice. Okay, so now I have this. I want to prove it, and let's start by seeing what we can do here. So the idea is I can put this on the other hand, on the other side, or I can put this on the other side by using the exponentials. And now, in order to not have exponents, I will write exponentials with an arrow. So let's put D on the other side, and let's try it like that. So this would be D, this operation that I have, the exponential, and all the other thing that I have there, which is At some point I will cheat, and I would like you to figure out where I cheated. D and B, and that's it. There is no other thing. So the line was kind of overly big. And now I have a disjunction, so less than something, so I can reduce it, right, to A being less than this thing, and A being less than this thing. So I'll try to do it fast, okay, so A is less than this thing, and also B should be less than this thing. And what am I using here? I'm using that, what this thing does. Okay, it's an upper bound, and it's the best upper. Oh, sorry, I'm using that it's the best upper bound. Does that make sense? Okay, so if it doesn't make sense, say it. I mean, okay, I take silence to mean it makes sense. And here I will do the opposite. I will take this D and bring it back to the A. And now I will have something like D meet A is less than D meet A joined with something, and this is already closed here, D meet B. So this, how do I close this? I have something less than equal than itself joined with anything. So here I'm using, then yes? No. I mean, I've seen this as an atomic thing is less than itself joined with something. But it's not the bestness, it's the doingness. I'm just using that it's an upper bound of its left side and its right side. I'm not saying that it's, I'm not comparing with other bounds, which is what happened here. So here it will be like the join, what it does, and actually it's the left-hand side. This thing, oops, sorry. What does this, what does this thing do? It's an upper bound of this, and it's also an upper bound of that. And here I'm using that's an upper bound of this. Okay, so this closed here, and similarly, the other thing will close as well. I will use again, I will take this D on this side, so it will be something like D meet B, less than equal to that thing. And that's it. And the question is, where did I cheat? This is what this does, but now I'm taking the right part, the right hand side, the right part of this thing. And it looks like I'm done. Okay, where did I cheat? Lazarus.
I don't think there is a rule that allows you to, if you have something like an implication to the right with
Okay, very, very nice. Oh, probably I cheated in one of those three, right? Because I didn't. So which of these could I actually do? If I look at the rule, it allows me to take the A from here and pass it to the left. Where did I do that? And the two top ones. So these ones are right. So this one is like the exp best, and this is the exp best. So what is this? If it's something, it should be something I should prove. And it's true that I can do that, but it needs some thinking and some arguing. I mean, a lot of times the rules that we have can be read, can be walked in both directions, applied in both directions, but what we have here is just this one. So if I want the other thing, I need to prove the other thing. So I should be able to prove in this case that if I have something like this, like I should be able to derive, okay, let's make this smaller. You don't need to read it right now, just need some space. So I would like to accomplish the following: C and A less than or B, and this should be should eventually manage to prove this when I only have as a hypothesis this. Ideas. Or let's get back to the ideas here, because I lost some minutes that are kind of precious for today. If I don't do it, it's not hard. If we have some minutes, we go back to this one to finish it off. But the idea is to use what you have already. You have exponentials, you have all those things. You just cannot directly go here. And you have meets and joints and all those things, and you use them and you finish this off. It's a small proof. We'll do it later on. What I want to do now is, since I reminded you of the exponentials, is see how this concept manifests itself in a categorical setting. So we should define what an exponential means in a categorical setting. And it's our first definition that we'll see in this class, and we'll see two of them today, the exponentials and what it means to be free. And both have the same kind of complication, because usually so far when I'm defining something, drawing diagrams, I'm always in one category. While here, I will need to say something that involves two categories. It's not as complicated as it sounds, so let's see how I can say those things. I will start with what it means to be free, maybe, because okay, let's start with what it means to be free. Maybe what I said is not exactly true for the exponential, and you will tell me that I'm cheating on what I said to scare you off. But okay, no, let's do the exponentials in categories. What should be an exponential object of A and B? Okay, so it's the same idea. It's something that if I take it together with something else, it can give me its output, let's say. And it encodes the idea of functions from something to something, or arrows from something to something. So what should be this be? Let's call it for the time being E. I have an A and a B, and I want to say what it means to be the exponential of A and B. So taken together with A, it should come with a way to produce B's. Okay, so I have a B here, and these things will be all the candidates for the best exponential. Things together with a map. I will call this map eval, because it evaluates think of this like a function from A to B. Think of this like an A, and what this does is takes this function, applies it to A, and produces a B. And I have to say that it's the best among all those things, because somebody else might come and say, okay, I have something. The candidate is I always write with a C, and I can tell you also how, if you join it with an A, combine it with an A, there is a way to go here. So this would be a different candidate for that. I'm not sure how to color like the candidates now, but the candidates are like objects such that equipped together, maybe I should do the whole thing as green, I don't know. Equipped together with, no, I will do it like that. Okay, so here is my candidate, and here is the other candidate. I want to say what it means to be the best candidate, and we have already seen this in order. It means that mine is like greater. It means that there should be an arrow from the purple to the green. What do you think is the notion of an arrow from the purple to the green? It's similar to what we did with the group objects, because there was a central object there together with its entourage. And in this case, the central object is E, and I'm saying E together with its entourage is like the best among all those guys. So, ideas. Manolis? And even more, there should be a unique arrow, because we're defining this with a universal property, so among all those things, it should be picked as the best, and and they will end up being, again, isomorphic up to unique isomorphisms, and this is like, okay, so there should be an arrow. Okay, But I want to draw an arrow. So, okay, this is the complication I was thinking about. It's not really a different category because I'm in the same category here. This will happen next in the free object. So I will make a copy of, because I don't have access to C and E independently here. I have C cross A, I have drawn E cross A, but where is C and where is E? So let's draw C and E in this obvious, on the side here. So I have C and I have E. So there exists a unique arrow here such that it makes the diagram commute. But look at this arrow, it doesn't mess with the diagram. But the thing that happens in this diagram, it will happen on the free as well, is that as soon as I draw something, something else gets drawn whether I want it or not automatically. It happened with the group object as well. I drew something from G to H, and a lot of arrows were drawn like automatically. I don't know how to do this with my tablet, maybe there's a way. But essentially, let's call it, okay, so you know that there are implicit for alls here, for all C, for all F, there exists one such thing. So again, this gives me a way to define functions from C to E. Given a function, in this case, from C cross A to B. So I will give it an indicative name. I will call it, I don't know, something like that. I will close the door. Because it kind of will end up being from this F. So like given any F here, there exists a unique F hat here that makes the diagram commute. What diagram? Where is the extra function? And what's the name of it? So here, my convention was thinner arrows for the automatic ones. I gained a function from C to E, and I'm claiming that the moment I'm drawing these arrows, something else also gets drawn automatically. Lazarus?
From C cross A to D cross A.
Exactly, and do we have... Yeah, yes?
It is the pair of F and identity.
Exactly, it's just not the right word you used. It's not. It's very common to confuse this. It's not the pairing. It's not the pair of this thing. It's the. I mean, technically, it's the product. So the pairing is like you have a common source, right? And you get the pairing of this. Here you have two functions from A to B and C to D, and you take the product of these. So this would be F hat, and here, which one? You said it? The identity. Okay. So whether I want or not, the moment I'm drawing this gets drawn as well. And now I know what it has to commute. And now the question is, has anyone figured out what's the name of this? Because we have met this. I will give you like a couple of minutes to think this. Think of what it does, what it takes. I mean, I'm asking for the hat as an operation. Take something and gives back something. And once I'm doing that, I get to name this, to give it an indicative name because it's defined by a universal property. So this is like, the name I will choose is this. Okay, small hint. Look at what you got. You got a function from here, from C cross A to B, and thanks to this arrow, you got a function from, what did I want to say here? Now I'm confused. I'm confusing my hint. Yes, okay. No, my hint works. You got a function from C cross A to B, and you gained a function from C to B to the A, which is encoding what? B to the A? No? Okay, yes, maybe?
I mean, based on the notation mostly, it kind of reminds me of a thing you would call an F-map.
Oh,
The actual
no, there are no I mean,
maybe it has nothing to do with this.
but which notation, how do you think of this?
Exponential, maybe because it looks like.
There is some kind of f-map here, I mean, because this thing here is a functor, so from this arrow to get this arrow, you f-map this arrow with this functor and you get the corresponding arrow from here to here. So even slopily, sometimes we don't even mention this, I could write this like that. And the idea is you should be able to figure out what I mean, because that's the source and that's the target, and this is different. But what did happen on the source and the target? This functor got applied. So obviously, I'm trying to apply the same functor here. And what does it do? It does exactly what Lazarus did. It does this. Oops, sorry. It does this. Okay. So here, there is an f-map here, which is this thing, like apply this functor. I hope we get what I mean by this. Apply this functor. Here is the argument, okay? So apply this functor on this thing. What do you get? You get exactly this thing. It got applied on the objects and got applied on the arrow. So there's an f-map here. But the f-map gets me from this to that. My question is, what's the name of the thing that gets me from this to that? Okay, so remember what eval does. It takes a function and an argument and it evaluates. It gives you the output. So what does this function do, this f do? What does it do? Okay, it takes a C and an A, and it maps it on a little b here. While what does this one do?
It's this step by step, I don't remember the name, right? It's the isomorphic behavior, how do you call it, between cross and then function carrying.
It's carrying. Okay, you said the name. Yes, this is scarification or descarification. I always confuse the words. It's uncarried here and it becomes carried here. So if I spell this thing like that, you will see it immediately. If I spell it like this, okay, this is what it decodes. And it's the same notation used in set theory. When you want to say the function space from A to B, you write it like that, or you write it like this, and indeed it's an exponential object in the category of set. So the idea is that it encodes this, this object here encodes functions from A to B. So you get, given a function from C cross A to B, you get a function from C to functions from A to B. Okay, so this is what permits you to internalize this idea, external idea of collection of functions from something to something. You have an actual object there that permits you to do that. And this sometimes is called lambda f, indicative of the situation, or like codification, or whatever. So there was a kind of complication here, and we'll see it a step further now that I will mention the free object, because I was drawing things and extra things were getting drawn. I was drawing things here. I was saying they have to commute. I have to pay attention to what gets drawn here. And it's something similar that will happen now with the free object. Any questions on the exponential? Yes?
I feel like I don't see why that's clarification.
Okay, what would you expect of the internalization of the idea functions from A to B? First of all, you expect them that if you take them together with an A, you should be able to say exactly which B comes out. And this is on the part of does. What does it do, the exponential? It comes together with this. So forget this whole thing is to define it universally. It's the bestness. Forget the bestness, let's focus on the dash. So, first of all, if you claim that around here I have some objects that can be used as functions from A to B, you should tell me how, if I give them any A, they will produce a B. So this is what eval does, and it's your job to give me eval together with this object. If you just give me an object and tell me this behaves like a function from A to B, I don't know what to do with an A. But you tell me this, and this is why, again, it's not just an object, it's an object with its entourage. Okay, so all this green thing starts to claiming that I represented the ideas of that. And now you have to defend like you are the best of these things. So if indeed you capture this, imagine someone coming here with an actual function from C cross A to B. Okay, so this F that this person came up with is an actual map in my category or in my function space, what you like in set theory maybe you think, or in type theory, whatever. You have an actual arrow here from A to B. So there should be a way from this arrow to factor through my arrow, which means that if you have a way out of any C and any A to produce a B, there should be a way out of any C to produce, like fixing the first argument, right? I should be able to fix a C and ask, now I should get a function from A to B. Since you claim that you can produce, that your thing maps there, you should tell me like how to do that. There should be guaranteed a way, it should be guaranteed that there is a way from any function like that to produce a function that first gets the first argument and then gives you back the remainder as an encoded object for the thing you claim you can do. So I'm not done with this. I need this bestness because now I can do clarification. So you give me C cross A F to B, and I will produce a C from, an F hat from C to the object that codifies functions from A to B, which we are calling B of A, and which I know how to use as a function from A to B because you have given it to me together with eval.
Okay, wait. I think I see what I don't see now.
Okay, okay.
I kind of see better, that kind of makes sense, but I'm confused because I feel like we're treating C at the same time as a set of thing of functions from A to B.
C?
C is of the same like nature as the we had initially, I assume. So if we're treating E or B to the A as functions,
Okay.
kind of treating C like it's supposed to be the same thing, so it should
Yeah.
be functions.
Okay, maybe I will help you here, I hope. But if you fix a C in big C, then this should correspond to a function from A to B. It should correspond to a function from A to B. Like for any little C that you pick and see, I should be able to get out a function from A, just from A to B.
Well, yeah, but then we're treating like an element of C like a function, and at the same time we're kind of treating it like the first coordinate of. Okay, yeah, I kind of see now. The first coordinate of a pair that we.
Yes, like a section, not a section, but how do you call it? I don't know.
So yeah. Okay, so basically you map every element of C to the function that sends.
To the function that expects the second argument
Yeah.
in order to produce the final output, which is exactly what purification does. Or disqualification.
Okay, so
No, purification, yes.
you see as both like a function and an element at the same time. Wow, that's weird.
I get what you mean. It hasn't troubled me, but yes, okay.
I kind of get it, but like, okay.
Elements of this, the idea is that elements of this, little c's, corresponds to functions that go from A to B. Because you map every little element of this exactly to an element of that, which are all the functions from A to B. It's like, let's give a specific example, like C plus A. This should be some kind of B. I mean, so this is the binary. Is it a good example or not? Yes, maybe. So as soon as you fix a number C, now you have the C plus, and now this goes from numbers to numbers. So I can see every natural number as a number, in this case, and I can see every natural number as a function, the function that adds this number to itself. So I think this is an example specific of how you can see something at the same time as an input to something, and as the function that by purification will be created the moment you fix the first argument. It's a good observation. I hadn't thought of that, but I think it's not so weird. I mean, it's expected out of purification. Purification does pretty much exactly that. It's like my catchphrase. We can see this on Zulip as well. But I mean, yeah, if you have something more troubling, bring it on Zulip. It will be nice to see it. We have a few minutes left to define what it means for an object to be the freely generated from something. It's an extremely important idea throughout algebra and computer science. A lot of times you want to say, okay, take these generators and give me the freely generated thing, and I would like to capture what this idea means. So there are a lot of descriptions you can find, and I want to start by reminding you what usually happens in like the free monoid or the free group when we want to define this and don't care about really understanding the idea of what free means here. You may say that the free, okay, so the idea is you have a set A, and you consider its elements to be the generators of something. And as we've seen like in the 2 classes ago, it's like I want to start operating with these things without without accepting any equations that are not forced on me by the axioms of whatever context I have. Maybe I like groups or monoids or rings or lattices, I don't know. So initially, I can think that first of all, the object I'm after, the freely generated group from the generators A, should at least have these generators in it. But I don't want to be so like strict and say this should be a subset of the freely generated. I'm doing groups and monoids. Let's do monoids. It's simpler. The monoids from A. So it's like wanted. I want to define a monoid out of the set A, and I want to treat the set A as its generators, and I want to say what I can generate from this. Okay, so instead of saying that A should be a subset of the monoid, I want to say, okay, there is a way to embed A inside this. So you don't give me just a monoid. You should tell me also how I can insert, this is called the insertion of generators, how can I insert A inside your monoid? And now that you've given me this, I can start wondering if it's really the free thing generated out of it. The essential part of the free monoid or the free group or the free whatever is that as soon as I have this, if I want to define a homomorphism to a different monoid, n, I only need to tell you where to map the generators. Let's say that A has, 3 generators, A, B, C. If I tell you, I want to define a phi. If I tell you, look, phi maps A to this element over here, B to this element over there, and C to this element over there, I'm done. You should be able to figure out all the homomorphisms just by knowing where these things get mapped. And if you've seen this before, you say, okay, it kind of makes sense because I know that like in the free monoid, every object can be written as a product or whatever operations you have there. If you have a group, inverses can be involved or stuff like that. So the idea is that, I want to capture this idea, that the essential property of the free thing is that in order to define maps out of it, it's sufficient to tell me what to do with the generators. And this is the kind of complication that I want to go through with you now, because I will be drawing things. Here, I was drawing things and extra things were getting drawn, but I was at least in the same category. So now I will need to involve 2 categories. And let's do it for monoids, and you will figure out how this generalizes to anything else. So the involved categories here is the category of sets and functions, and the category of monoids. I never know if it's better to do it like, okay, let's do it like that. Top and bottom. The fact that I have a functor from monoid to set, which we have met like 2 classes. Can someone tell me what functor I'm thinking about? And hopefully what's its name? Yes? The forgetful functor, which is usually called U, and not F, because F is usually called the kind of the opposite of this, which is we are defining now. F comes from the word free, and it's kind of dual, adjoint is the right word, to U, which comes from the word underlying. So the idea is you get a monoid, you get the underlying set. You give a homomorphism from monoids to monoids, you get the underlying function. Okay, so anything I draw in monoid will have a shadow by forgetting stuff being drawn automatically on set. So what is the thing I have? First of all, I have a set because I start here. Do I get something automatically on the monoids the moment I draw A? For the time being, no, because my functor goes from monoids to the shadows in sets. When I'm done with this construction, I will end up creating a functor in the opposite direction, which will exactly define for any object set its free, the free monoid. Okay, so I will have a way to draw something below and have something above up here. But for the time being, what I have is anything I write above casts a shadow on what I write below. So I have an A, and I'm looking, this is what I want, to define a monoid with a certain property. It will be the freely generated monoid out of A. So I'm looking for a free thing, and I will end up calling it, because it will be defined by universal properties, so it will be unique up to unique isomorphisms. So I will adopt the notation like this. The idea is that you have the right to have a notation that depends, like as if it was a function here, as soon as you have this uniqueness, and I will have it. I don't know if you want to start with, okay, let's start with an F and then I will replace it. I usually do that. Okay, so I'm looking for a monoid F, okay, which has something to do with A, but in order to be a free monoid, it doesn't come by itself. It has to come with a way to embed, with a way to insert A inside it. So I will write it here. So it doesn't come by itself, it comes together with an insertion, which means something like that. And what should I write here? I mean, this F should be kind of calligraphic. I should write just an F, not calligraphic, if you like that. But technically, the notation we have for the forgetful thing is we get the absolute values. So, are we okay so far? So I'm trying to produce what the free thing does. First of all, it's a monoid, so it's here, and it comes together with a way to embed A inside its carrier set, because A is just a set, it's not a monoid. So I need to see its shadow here. This is the carrier set of this monoid that will end up being the freely thing, and it comes together with this ins. So if I want to color the whole thing, because again, it looks like this is the free object, but again, it doesn't come by itself, it comes together with insertions into its carrier set from A. Does that make sense? Okay, so now we have to see what it means for this to be the best of all those things that have this property. So some other person comes and say, hey, I have a monoid that does this. I have a monoid and I have a way to embed A inside my monoid. Let's call the other candidate monoid C to respect traditions. And C doesn't come by itself. As soon as you draw it there, you have this. And the person says, okay, but I have you covered because I also have a way to embed A there. So essentially I should move my A here. Okay, so let's do it like that. This was the original one. This is the green. Okay. And the other person says, okay, I have a way to do that. I have a way to insert A inside this. There's a monoid here, and I will tell you how to insert A inside it. What does it mean for my monoid to be the best? It's either initial or terminal. In this case, it will be the initial, and it's like, oops, sorry, get this. I need to say there's a way to go from the green to the purple. What is this way? Remember, there is an implicit for all purple stuff, and it's kind of similar to what happened in the exponentials. The idea is, as soon as you tell me how you give me a function from A's to C's, I should be able to figure out what I'm looking for, basically for the idea of what should be an arrow from green things to purple things. Yes? Wait, well, let's speak categorially. Okay, I know isomorphism is a categorical word, but I mean, let's look at it as a diagram with possible arrows. What would it mean to go from somewhere to somewhere in this case? Your object, the protagonist, seems to be this thing here. Lazarus, what were you about to say? Or nothing?
I don't think it's a correct answer.
Okay, you want to withdraw it or want to? Okay. Konstantinos, you have an answer? There should be like an arrow from here to here. But as soon as I draw something, I get a shadow there, and this gets me what has to commute. Such that the shadow of this thing, which is automatic, this little diagram should commute. And this captures the idea, okay, what does it mean that it's freely generated? You don't get extra equations. If you map things together, you would be forcing every interpretation, every homomorphism after that to collapse with these things. But you have like A, B, C in my example. If you map A and B to the same thing, then any other homomorphism that goes through yours will have no way to distinguish between these two. While now you want to capture exactly the idea that, look, how do I get homomorphisms from a monoid, from the free monoid to anything? The free monoid is very good, because in order to get homomorphisms out of it, it's enough for me to give me a little function just from the generators to your monoid, okay? And then I can extract from it an homomorphism in a unique way, so I'm done defining the homomorphism out of the free object. And this, as soon as I do that, it means that I have another functor that goes the other way around, and I will call it F. And we don't have time to see this, but the idea is that one, in a way, is kind of the dual of the other. As I said, the correct notion is adjunction. And again, this is a notion that I think is quite informative to see it first within the context of orders and then understand it in the richer context of categories. Essentially, I will just say this and wrap things up. Essentially, I mean, what would this correspond? This relationship between this and this correspond? They are not inverses. If you get the free and then the underlying set, you will not end up where you started. I mean, take a single object, generate the group out of it. You already have a group with infinite elements. Then see what the underlying set is. It's already a different set because it has an infinite number of elements. So they're not inverses, but in a sense, they have this kind of relationship, which is called adjunction. It would be the next big thing to see in categories. We will not do it. But a small teaser, let's say, nothing to do with categories. If you are you have a poset P and a poset Q, and you have an object here and an object there, how do you compare them? Each poset tells you how to compare elements in itself. The other Q tells you how to compare elements in itself. If you have one guy here and one guy over there, what should you have in order to say that I can compare them? Definitely, if they are isomorphic and you have an isomorphism, you can translate whichever you like to the other thing, and you can compare them. But this is too strong. You should be able to have a way to compare demanding less than an isomorphism. And as we have seen, these two things are not one inverse of the other, and still we can have some kind of comparison between one world and the other. So the idea is that you have a pair of maps here, which being posets, these are monotone, let's call them F and G, such that the following holds. Whether you take A and map it to to Q, so you have F of A here, or if I take B and map it with G over there, we have A will end up being less than or equal to GB if and only if FA will be less than or equal to B. Careful, this less than or equal goes to P, and this one is on Q. So I'm demanding the least I should demand in order to have a meaningful sense of what it means to compare these things. So essentially, you will have an arrow here, if and only if you will have an arrow here, and essentially this means that you can translate things like what do I have here? From this, you can go to no? Is this correct? I think it is, yes. To this. Maybe I messed something. Oh, I will delete this. Okay. Yeah, so we're kind of out of time. I just gave you some teasers, well, not spoilers, like maybe little baits if you want to see something more towards this direction. We didn't have time to see the identity well. We have only seen how we can prove things by reflexivity. We haven't really seen how to use it. And there the idea would be to describe that equality is like a congruence with everything. Final question, what does congruence mean? I said 1 hour for today. I still have 6 minutes. I realize that we started 15 minutes past. Okay, so what's a congruence? And what's a Greek word for congruence? I have no idea. Equivalence. Isotimia, maybe. Has anyone heard this thing as a...
I think that's how we call it in number theory, like isotimia or belief.
So, okay. Isotimia, okay. Maybe, congruence. What does it mean? What's a congruence? Okay. We will not end this semester without seeing the definition of a congruence. So it's weird because you have used this word tons of times, right?
In what context?
In any, I mean...
They belong to the same equivalent class. That was the idea.
You are only looking at equivalence classes then, and equivalence relations.
In number theory, we said that two objects are congruent if they belong to the same equivalent.
They are congruent if they satisfy a congruence relation, okay? In number theory, you have a very specific congruence, and this is, I'm getting pissed. Okay, because this is always what happens. You see a definition, which should be a theorem, and the definition you see in number theory, you say what it means for A to be congruent B modulo something. I will put it here. Modulo, and it's like this is what congruence means. No, whether it's a congruence or not, it's a theorem. I mean, does it satisfy the properties to be a congruence or not? So congruences are very special kinds of equivalence relations. So first of all, it has to be an equivalence relation, and I'm sure you prove this in number theory. Like prove that A is congruent to A modulo M and whatever. But it's an equivalence relation. The important thing of a congruence is that it's compatible with all operations lying around. What does it mean compatible in number theory? It means that if you have A plus B, and this is congruent to, I'm not writing it properly. So like if you have A congruent to A prime and B congruent to B prime, then A plus B is congruent to A prime plus B. So you can do arithmetic pretty much in number theory. But this has nothing to do with numbers. I mean, as soon as you have any operation, as you have anything algebraic there, you have operations. And as soon as you have any equivalence relation, it is called a congruence if it is compatible with all operations that you have. Which means that you treat it like you want, this thing will be a congruence if from this I can guarantee this. So equality is like the best congruence in the sense, or the worst, depends on the point of view, in the sense that it's compatible with anything that has already been defined, and anything you define should continue being compatible with equality. So the challenge in defining equation is how do you say this? We will not do this. But okay, I had it in my plan to check this thing about the definition of congruence. So does this definition make sense? So after you define this relation in number theory, you should say, I will prove that it's a congruence. With which operations? The ones you have in the integers, it's like plus, 0, 1, times, and that's it. Not with exponentiation. I mean, it's a common rookie mistake to say, I will replace congruence with congruence when you have exponentiation. If you have passed number theory, you know this, you cannot do that. So it's not congruent with anything you define. This would be the equality. But it's congruent with the principal operations that are lying around in the number theory, which is plus and times. Okay? Does that make sense? Okay, that's it, I guess. There are still some days left in the semester, and I will leave Zulip open if you want to make any statements or solve things for people who are expecting a mark on this course as well. I'm not sure when the semester officially ends. I think it's beginning of July or something. I don't know. But let's see. I will declare official date of finishing this course on Zulip, and it will stay alive and counting for marks as well for this period. So that's all.